So I'm at the EPA regional office in Denver. I work with Western states on photochemical modeling to support their state implementation plans for ozone, PM2.5, and regional haze. And I should say again that this presentation does not reflect EPA policy guidance or recommendations. It's my personal opinions. And I'm going to try to list some of what I see as the priorities and how HAQAST can and the remote sensing products generally can be helpful to states and EPA regional offices as they develop state implementation plans. A lot of these topics have already been discussed on the previous panels, but I'll just try to reinforce their importance. So one of these is getting better estimates of biogenic emissions and background ozone levels. For example, using formaldehyde measurements to improve estimates of isoprene emissions. The OMI data lacked the sensitivity and hasn't been very useful in the past, but hopefully, with TropoMI and Tempo, we'll get better estimates. Also, some of the techniques to assimilate ozone data from the lower stratosphere and upper troposphere, those can be very useful for improving, the model accuracy of the model contribution to ozone, coming from the lower stratosphere. We also need accurate estimates of lightning NOx and soil NOx emissions. There are flash count products for lightning NOx, but not all the states can afford those. They're very expensive. So making these types of improved estimates available to the larger community would be very useful. We'd also like to better understand missing or uncertain domestic anthropogenic sources of emissions, and some of these include oil and gas emissions, agricultural activities, consumer products, mobile sources. So there's the question of whether satellite assimilation techniques can help improve U.S. anthropogenic emissions. And I included a citation here from some of Dan Goldberg's work looking at cities and large power plants. I think the question going forward is, will this work on smaller sources like individual oil fields or other source categories that might be poorly represented in the current emissions inventories? And then international transport contributions to ozone are also very important. The Clean Air Act provides regulatory relief under Section 179B if states can demonstrate that they would have attained, if not for international transport contributions. For non-border areas, this requires global and nested high-resolution regional scale photochemical modeling to estimate the international anthropogenic contribution to domestic ozone, specifically on high ozone days, the days that caused the failure to attain the NAAQS. And so I think Jessica will have a slide that shows how those products can help with that assessments of international transport contributions. The Clean Air Act also provides regulatory relief for exceptional events for ozone that can be from stratospheric intrusions or from wildfires. A lot of the folks on the call today have been very helpful with our stratospheric intrusion work group that's been using a variety of modeling and satellite data products to help identify these stratospheric intrusions. And I linked to the total ozone column data product there that is useful. I also look almost every day at the NOAA hazard mapping system fire and smoke product. And there's a slide there from yesterday, a day that we exceeded the ozone NAAQS in the Denver Front Range. And these are helpful to get a sense of days when fires might have contributed either to ozone or PM2.5 or regional haze. And we're very interested in day-specific model performance evaluations, specifically for the high ozone days that cause states to fail to attain the ozone NAAQS. And I have a slide here of a model simulation with the ambient monitoring data shown in the diamonds. This is at 10 a.m. on May 30th, 2011. And you can see high ozone concentrations in rural and remote areas from New Mexico through western Colorado up into western Wyoming. So this is a day where there was obviously a stratospheric intrusion of ozone contributing to these high ozone values. And we can exclude days like this if we can identify them. The data actually gets removed from the regulatory data set that EPA uses to track attainment of the ozone NAAQS. And that also means that we're not necessarily interested, or we don't really care about background ozone concentrations on days like this, because these days do not cause the states to fail to attain the NAAQS. And so what we're really interested in is model performance on days with photochemical ozone episodes with urban air pollution and estimates of background ozone on those days, not on the days with stratospheric intrusions or wildfires, which are going to get excluded from the regulatory database. And then my last slide, this is something that I'm especially interested in. Can high-resolution satellite data sets help assess multi-pollutant exposure and improve epidemiological health effect studies? We use ozone as an indicator of total photochemical oxidants, but it's not always a good indicator of urban air pollution. Like, for example, the previous slide where I showed a stratospheric intrusion day, that's a day with high ozone, but very, very low concentrations of other photochemical oxidants. And if you look at urban areas, especially urban core areas, they can have low ozone concentrations because of titration by fresh NOx emissions, but very high concentrations of other oxidants. So epidemiological studies that only use ozone, especially core spatial resolution ozone, may have limited value. And I included a link here to the most recent integrated science assessment. It's one of the criteria documents developed by EPA for the most recent ozone NAAQS review. And if you haven't looked at that, take a look at that document and the epidemiological studies. And let's think about how we can do better epi studies using multi-pollutant exposure, hopefully data sets that we can get from high-resolution satellite products like Tropomi and Tempo. Okay, thank you.
So I'm going to talk a little bit about how satellite data can be used to inform estimates of background ozone. Satellites do measure ozone, but it's not possible to use the measurements directly to inform background ozone for two primary reasons. And the first is that satellites don't measure surface ozone. So they provide either a total column measurement in the case of instruments that measure in the ultraviolet part of the spectrum, or they produce a measurement that's sort of heavily weighted toward the mid-troposphere for infrared instruments. And so, you're really not seeing the surface with satellite measurements. The second reason is that, as for any measurement system, including surface measurements, it's impossible to separate background ozone or ozone from particular sources directly from the measurements. However, as I'm showing in this schematic here, we can assimilate satellite measurements of ozone and its precursors into models, and then use the models to quantify background ozone and attribute it to various sources. And the assimilation system that we use at JPL, at the NASA Jet Propulsion Laboratory, is an ensemble common filter approach. And so what that means is that in the end, we get fully self-consistent emissions and atmospheric concentrations. And so what we do is we ingest satellite data from multiple instruments from multiple constituents. So we're bringing in NO2 measurements from OMI and Tropomi, SO2, CO, and those go into not only informing the NOx, CO, and SO2 emissions in the model, but also to informing surface ozone concentrations. And then we are also bringing in upper troposphere and stratospheric ozone from MLS, as well as nitric acid. And then we can also assimilate mid-tropospheric ozone from infrared instruments, such as the tropospheric emission spectrometer. Or we also use a combination of the atmospheric infrared sounder and OMI, and that provides a nice mid-tropospheric ozone product as well. So together, the measurements of ozone and its precursors all sort of feed into the model estimates of surface ozone. And so when we do that, we can see, first of all, that there have been huge shifts in the distribution of NOx emissions over the satellite record. And so these are the NOx emissions trends from our assimilation system. So these are informed by the OMI NO2 measurements as well as by atmospheric concentrations of all of the species. And so you can see that from 2005 to 2010, we had big declines in the US and in Europe. And I should say that over here are the sort of country scale integrated changes, percent changes from 2005. And then from 2010 to 2015, during that earlier period, we had this big growth in emissions in Asia, in particular in Eastern China. From 2010 to 2015, those Chinese emissions really dropped off, but we started to see an increase in emissions from India as well as some from the Middle East. And then in this most recent period, there's been more of a mixed bag, but again, still growth in emissions from South Asia, sort of a leveling out of the decreases in China. And we've also had a leveling out of declines in NOx in Europe and the US. And so the question is, what impact have all of these changes had on background ozone in the US when you look particularly at these changes in East Asia, where we're getting a lot of international transport from there to the western coast of the US? And so we've used the JPL assimilation system to do a series of sensitivity studies, and these are the results. So this is results for 2012 over the South Coast Air Basin that encompasses Los Angeles. And the blue lines are at 750 hectopascals, and then at the surface, this is the total contribution from China to ozone in the South Coast Air Basin. And so at the surface, the peak values are about 3.5 to 4 ppb in the spring, are coming from East Asia. The red line down here, however, is the contribution from the increase in emissions that we saw in China from 2005 to 2012. And that was about a 20% increase in NOx. And all of those big increases in NOx that led to all sorts of air quality problems in China have only changed US ozone by about sort of 0.3 to 0.4 ppb. This is for the South Coast Air Basin, but we get similar results for the entire EPA Region 9. And then here is a plot of, at 750 hectopascals, the change in ozone associated with the decreasing Chinese emissions after 2011. So you can see that as we go from 2012 all the way through 2016, we have less and less ozone coming over from China. But note the scale down here. Again, these are sort of less than half a ppb changes, and they're even smaller at the surface. This is, again, 750 hectopascals. And then over here, we have the contributions from China, India, and the Middle East. This is the change in the contribution from each of those countries from 2005 to 2011, as shown here, and then from 2005 to 2016. So we can see early on the increase in the Chinese contribution, and then in the most recent period, a decrease in that contribution. Despite the fact that we had these large emission increases in India and the Middle East, we don't see much of a change in how much ozone is coming to the US from those countries. And that, when we look at the model, that's really because most of the air that's transported from South Asia goes to the south of the US. So it's not really impacting background ozone in the US. So as part of the HAQAST Tiger team on background ozone that I led, we were generating boundary conditions for regional models to help with their simulations of background ozone as well as international transport. And so we were really interested in particular in sort of what's coming across the ocean into the US. And so this is a plot from the free running model where we haven't assimilated any information. And then this is where we have assimilated only precursors of ozone. We haven't actually assimilated any satellite measurements of ozone. But these are satellite measurements of ozone from the AirZomi instrument inside this box, and this is for April 21 to 30, 2016. And you can see that they indicate that there should be this plume of high ozone air in the south part of the box, and then another sort of region of enhanced ozone in the middle part of the box. And so you can see that the assimilation really captures those features, even though we're not assimilating any ozone, we're just really changing the precursor emissions in Asia. And so you can see here that that has a big impact on what the ozone concentrations are in California. And then these are just comparisons to ozone sondes from the California baseline ozone transport study that were taken along the coast trying to look at baseline ozone coming into the US. And so here the model is in blue and the assimilation is in red. And so you can see that we're really getting pretty big improvements in the upper troposphere in particular. And that comes from the assimilation of the stratospheric ozone measurements. These are now satellite-informed estimates of background ozone. So this is the monthly mean background ozone for April of 2016. So we estimate background ozone using the optimized emissions from the assimilation and then zeroing out US anthropogenic emissions. And then we're still looking at the differences in what we would see as background ozone between the free running model and the assimilation. So I don't have results for that yet. But you can see here that in California, background ozone peaks in the spring, and it makes up almost all of the ozone at 750 hectopascals for more than half of the year. At the surface, you can see the additional influence of local emissions, obviously, but the seasonal cycle of background ozone is the same, and it still makes up a large portion of the surface ozone in the spring and winter. And so now I'm going to hand it off to Arlene, who's also got some exciting results on background ozone.
Jessica. So Jessica was just talking about the importance of boundary conditions for background ozone, and particularly global models feeding into regional models. And so that raises the question then of how good are these boundary conditions? And one of the ways that we can evaluate that, as Jessica showed in her talk too, is with ozone sondes. And so as part of the Tiger team on background ozone that Jessica led, our group used some information that was generated by Ryan Stauffer and Ann Thompson at NASA Goddard Space Flight Center, in which they had applied a machine learning approach to analyze ozone sondes and distill them into 9 kind of characteristic patterns or nodes. And those are the different colors that you're looking at here. And so what we did was to show that then we can go in and sample, in this case, a global model, GeoSchem, on the days when each of these patterns was observed and see whether the model kind of gets the same features. And one of the things that jumps out from this figure, obviously, is that there's a big difference in the variability that you get when you have 350 vertical levels versus 47 vertical levels. But we were pleased to see that the ranking across the different patterns shows some correspondence in the model to what comes out of the sonde analysis. And the excitement here is that to the extent that we can link each of these patterns with a specific process, for instance, associated with stratospheric influence or Asian transport or local pollution, then we move towards the ability to evaluate these models in a more process-oriented way and understand not just what the biases are, but why they're biased. So with this same model, the GeoSchem shown here. There we go. This next figure is showing some highlights of an analysis that involved a whole bunch of sensitivity simulations in which individual sources were zeroed out. And what we're looking specifically here is kind of classifying days into those high ozone days, in this case, lumping the top 10 ozone days from each summer. We're focused here on the Midwestern region, but the paper cited here does this for the lower 48 states for all 10 EPA regions. The red are the high ozone days as compared to the blue, which are just the average of all summer days. And so we have to the leftmost here a US background estimate, which is attained by zeroing out US anthropogenic emissions in the model. And the next category here is an estimate of the contributions from US anthropogenic emissions. Perhaps not surprisingly, the highest ozone days in the eastern U.S. tend to be associated with enhancements in U.S. anthropogenic and biogenic VOC emissions. What was interesting is that we found that actually the intercontinental influence was lower. In other words, the highest ozone days are not necessarily associated with enhanced transboundary transport, but regional production. And so we also had the opportunity with these simulations to look at year-by-year variability. And so I'm just keying in on a few highlights here. But the black line is showing this ozone from U.S. anthropogenic emissions for the Mid-Atlantic and the Midwest from 2004 to 2012. And we do see this kind of downward trend associated with reductions in ozone precursors in this region over that period. The U.S. background estimates are shown in red, and they vary from year to year, and there's a sense of an uptick in the later part of the time series. And in particular, I'll remind you that summers 2011 and 2012 were pretty hot years. And in the model, we attributed much of this variability in the background to variations in natural ozone that was estimated by zeroing out all anthropogenic emissions globally. And so this includes, for instance, biogenic VOC emissions reacting with natural NOx such as soil NOx. And so just kind of emphasizing Gail's point that it's important that we really have good emission estimates for all of these different sources, and that is a place where satellite data can come in. I just wanted to emphasize that part of the challenge for sort of the background ozone, a lot of the challenges that apply to background ozone also apply to regional haze. And that is that our stakeholder partners would really like to have well-evaluated low error boundary conditions, and in addition, source attribution, in this case specifically for the breakdown of haze components on the most anthropogenically impaired days. And an important point here is that both the implementation of the regional haze rule and the ozone standard involve, under the Clean Air Act, the regulatory framework that is pinned directly to the high quality on-the-ground monitors. And just to reiterate what's been said in many panels, we don't actually directly observe either surface ozone or surface haze from space. And so the way that we bring in satellite data really comes into the model evaluation, constraints on emissions, and sort of getting a better handle on the attribution of sources. And so I wanted to close by just mentioning that in addition, we have now ever-growing records of satellite data, for instance, from the OMI-ORA satellite that has provided daily information about tropospheric column, nitrogen dioxide, and formaldehyde for well over a decade now. And these long records are important because even though on a day-by-day basis there's a lot of noise, we can't retrieve when there are clouds, when we start to have long-term records, we can mine them for information about how some of these species respond to climate variations. And an example here is for drought, where we can composite over drought. And so I just want to highlight that this poster is available if you're interested to see what we were doing on that front. And at this point, in the interest of time, I want to pass over to Tom, who I think is going to provide us with a nice forward-looking perspective to close out the panel.
Good afternoon. I'm trying to clean up behind three awesome folks. I really appreciate the chance to participate and the great work of Tracy Gagan and Paige in making this showcase work. And with the situation we have now, it would have been great to be together. So I'm going to briefly comment on some aspects of the very helpful HAQAST background ozone Tiger team work that Jessica led, and just illustrate how for sources in air quality planning to improve air quality, the problem statement comes from the ground-based monitors, as Arlene just mentioned. And it's sort of amazing when you think about ozone. So air quality looks pretty good in Gothic, except for the stratospheric intrusion, and we're seeing a lot of fire, as Gail and others have mentioned, and then millions of people, live in various degrees of a PM ozone smog. So, drawing heavily on the work that I did with Dan and Arlene and Gail and Baron and a number of other folks, Ted, on this 2018 assessment. So I think the way I think about the HAQAST background ozone as an example of the challenges in front of us is that we really need remote sensing information assimilated and processed and made available to layer better understanding of the challenges in front of us. We see, as we clean up the air in the U.S., we see health effects at lower and lower levels. U.S. emissions have been declining steadily for 50 years, and that's actually likely to continue. We're in the West, we're closing over a third of all the coal-fired power plants in the Western grid in the next 10 years. So, because there's so many renewables online, the climate is changing. Fire and drought and dust all explain that, and of course we get things from other countries in the context of the global economy, and so those will lead to emissions. So those are reasons that we need a top-down view, but we need to process information in such a way that we can sort it into aspects that matter for U.S. agencies. They inform U.S. policy abroad. They inform economic activity and incentives. And I just want to stress that, a big fraction of the ozone that we're seeing at these ground-based sites that define the problem, as Gail mentioned, are, mostly not of local origin. So we can work on the interstate transport, we can work on the local production, but most of the signal is not controllable. So we really need the kinds of tools and what we've learned, started building the case for in the background ozone team for explaining the lower two-thirds of this stacked bar chart. And remember, too, if I might, that Gail's point about we have a Clean Air Act that every 5 years EPA is doing the best review they can. So the current ozone standard is the current one. That standard can change. It was recently reaffirmed by EPA at the 70 ppb level. So that's, for the foreseeable future, that's the target we're aiming for. An example of the challenges is that we've been working on some of these topics for a long time. I was very appreciative of Jessica's slide about, assimilating remote sensing and informing model performance there as air masses enter the Western U.S. Through the Cabot study and other things. So the Crestline monitor and the Denver camp monitor have been operating for a very long time, as this graphic shows, and strategies in the Los Angeles area. These are both high elevation monitors, relatively speaking, shows a dramatic decline, and the Denver one is much flatter, and there's a variety of information that we can only get or we can only understand well from remote sensing and assimilation into models. So a number of other panels have discussed issues with population growth and exposure, and there's certainly seasonal variation. But this is a problem because once an area violates the ozone standard at the ground-based monitor, it remains in that condition until local controls are sufficient to achieve the standard. So many of these areas are in chronic long-term non-attainment. We need to better explain the non-local contributions. So I'm very excited, as many folks in the NASA world and certainly in HAQAST know, about the amazing constellation of upcoming deliverables. I can't even really talk adequately about all this information, all these kind of cartoons of what's going on, but we have, GEMS already, flying. We're so looking forward to TEMPO with its sharp time, space, and chemical signature edges that we've never had before over the bonus, and so we're just very excited. So I'm not going to try and touch on all this, but I just want to emphasize how beneficial I found the HAQAST process in terms of interacting with the researchers who are really studying these issues. And I look forward to a next generation of work products and routine data deliverables, from these fine remote sensing platforms that are more usable, even more usable by state and local and EPA air quality agencies. So I'll leave it there and be happy to join in the Q&A.